Okay. So today we have a master defense by José Antonio Almanza. The work has been supervised by Roberta Zambrini and Gonzalo Manzano, and it's about quantum thermodynamics, I guess. And I think that you have around 20 minutes. Yeah, 20 minutes. And then the committee will make some questions about your work. Okay, thank you very much.
Well, hello everybody. Thank you all for being here. My name is José Antonio, and today I'm going to present my master thesis, which is entitled The Effects of Coherence in Quantum Absorption Refrigerators. I want to start this presentation with a little bit of history, more precisely the history of this man, Sadi Carnot. Sadi Carnot was a French military engineer that lived in the 19th century, and he wondered about why the English engines were much better than the French engines. In the way to solve that question, Carnot realized that the particular performance of an engine depends on the details of the fabrication. The limits of this performance don't depend on such details at all, and he realized that this limit only depends on the difference of temperatures between the machine operates. So why I am telling you this history is only because I want to emphasize the Carnot thinking and make some kind of extrapolation for our time. Nowadays, we are able to measure and to manipulate smaller and smaller systems. We are able to manipulate systems from the size of an atom. So now we are in the position of making like a new question, like the one that Carnot do at his time. And now this new question is, what happens if the working fluid is a quantum system? Okay, this is not an easy question to solve, but we are trying to avoid that in the work. And for this, we are going to split this question in two different questions. One is, what is the effect of coherence in these thermal machines? And the other one is, if there are machines of this type that are better than the others. These two questions defines the two main blocks in which I'm going to divide this presentation. The first block will be about the thermodynamic operation of the system, and the second block would be about how we can optimize the performance of the thermal machine. Okay, our starting point is this article from 12 years ago, in which the authors presents a model of an absorption refrigerator, which is composed by a quantum system. And this is a model that we are going to use in our work. So, but why this model? Why an absorption refrigerator? An absorption refrigerator is a thermal machine that can operate autonomously without any external source of energy or coherence. So, since we are interested in see the effects of coherence in the thermal machine, a good starting point is to study a system which is autonomous. Okay, now here I show you the schematic representation of the quantum absorption refrigerator that was presented in the paper that I already mentioned. It is composed by 3 different qubits that are interacting with 3 different thermal baths that are fulfilling which temperatures are fulfilling a relation like that. And then we have also an interaction between the 3 qubits which is given by this interaction Hamiltonian that you can see here. So now we are in the point to make the question of which dynamics have the system, or what is the equation that can define the dynamics of the system. Okay, since we are considering a quantum system, the most common and natural answer will be to say the Schrödinger equation. But since we have thermal baths, thermal environments, it's not the most useful approach. The most useful approach is given by the formalism of open quantum systems. Because more precisely, we know that since our system have a Markovian dynamics, which is the case that we are considering here, we can define the dynamics of the open quantum system in terms of what is known as the Lindblad master equation, which is this equation that you are seeing here that have 2 main terms. One that defines a smooth evolution into an unitary evolution into the Hilbert space of the system generated by the Hamiltonian of the system, and other terms that are called Lindbladians and take into account the irreversible effect that the environment has into the system. So Now I want to briefly comment the two main approaches that we take in the thesis to solve the Lindblad-Master equation. One is the full counting statistics, and the other one is the well-known quantum trajectories. The main idea behind the two approaches is the same. We are going to consider that we have a certain measurement apparatus in the environment that allow us to know when the system and the environment change energy. But the difference is in how we use the conditioned state of the system. On one hand, in the quantum trajectories, we keep the conditioned state of the system, and by doing that, we can define the dynamics of the open quantum system in terms of stochastic trajectories. By doing that, what we obtain is that we can calculate numerically, for example, the probability distributions of heat or any quantity that measures the energy exchange between system and environment. And on the other hand, in the full counting statistics, we are not going to use the conditioned state of the system. We forgot the conditioned state of the system, by doing the Fourier transform that introduce a new variable, which is called quantum counting field. Sorry, and we will have one counting field for each thermal bath. In our case, there are 3 counting fields, and by doing that, we can arrive to what is known in the literature as a generalized master equation. But here, the usefulness of the quantum trajectories is pretty clear. But why to use full counting statistics? Why to solve a more difficult, with more variables, master equation? Okay, the advantage of using full counting statistics is that we have results in the literature that like the one that I show you here in this paper, that states that by solving with some methods, by solving the generalized master equation, we can have access to analytical expressions of the cumulants associated with the distribution, with the probability distribution of the energy exchange between system and environment. We have access to, for example, the main value of the heat flux between system and environment, and also have access to its second cumulant, which are the fluctuations in the system. That plays a really important role in microscopic systems and a more important role in quantum systems. Okay, now by applying this method that we have here, we can pass to solve the dynamics of the system. Since our system is a thermal machines, we are not interested in the transitory regime. We pass directly to solve the steady state. The steady state is given by as a solution of this equation, which is a matricial equation. So here we have 8 equations for repopulations that are the diagonal elements of the density matrix, and then we have also 56 equations for the non-diagonal elements that are called coherences. But we don't have to solve all these equations because in the steady state we know that due to the effect of the coherence that the environment produces into the system, almost all the coherence will be 0. It can be shown, and we do that in the thesis, that in the steady state we only have one non-zero coherence in the system, which is the one that connects the 2 states that are related by the interaction Hamiltonian. And we also show that this coherence is a pure imaginary number. So now we can rewrite the dynamics of the system as this matricial equation, in which now the vector P only depends on the 8 populations of the density matrix and only one coherence. Okay, now applying the polynomial, the characteristic polynomial approach that I already showed you, we can compute the analytical expression for the different heat fluxes between the qubits and its thermal baths. More precisely, we can compute the heat flux between qubit 1 and thermal bath 1, which is called normally in the literature as cooling power. Here, the convention that we are taking is we are considering as positive the flux of heat that is entering into the system. So here we see two different main regimes, one in which we have a positive cooling power and correspond to our system operating as a refrigerator, and the other one in which we have a negative cooling power that corresponds to the system operating as a heat pump. And in the middle, we have the branch in which we pass from one regime to another, that is called the the cooling window. Okay, now we can compare the value of this quantity with the amount of coherence that we can find in the refrigerator. So, okay, here we have, for the same values of the energy gaps and the temperatures, the amount of coherence that the system has. As you can see, it exists a clear relation between the amount of coherence that we have in the system and an increase in the cooling power of the system. But we can go a little bit further, and since we have analytical expression for the heat flux, we can see what's the entropy production of the system. Here we compute the entropy production of the system by using the standard expression for the entropy production coming from a standard classical thermodynamics, and we plot here the entropy production in the system, and we see that we find also a clear relation between the amount of coherence in the two regimes and presence of high fluctuations or high entropy production. Okay, but as we say before, we also have access here to analytical expression to the fluctuations in the system. So we can see what is the relation between coherence and the variance of the cooling power, for example. As you can see here, it is not clear that exists a relation between the amount of coherence and higher or lower fluctuations in the system, but we can see what happens with relative fluctuations. For this, we define this quantity that we call precision. And now we can see what happens with the precision. And in this case, we find again a clear relation between a presence of coherence in the system and an improvement of the precision in the thermal machine. So at this moment, we have seen the net effect that the coherence have in the different main thermodynamic outputs. So we can pass to test our quantum thermal machine. How can I test my quantum thermal machine? Well, I can try to violate a classical bound. So this means that my quantum thermal machine can do something that a classical thermal machine cannot do. Okay, so as in this paper, for example, in which the authors sees that a quantum thermal machine is able to violate the thermodynamic uncertainty relation. But what is the thermodynamic uncertainty relation? The thermodynamic uncertainty relation is an inequality that was derived in the context of classical Markovian jump processes, and relates the variance of a current in the system with the mean value of this current and the entropy production rate in the system. We can see more clearly what is the thermodynamic uncertainty relation telling us if we rewrite the expression by using the precision. Oh, sorry. As you can see, the thermodynamic uncertainty relation is telling us that the precision is bounded by above for the entropy production. So at a certain value of the precision, in our system, we can only be more precise if we dissipate more energy. So now we are going to test this inequality in our system. For this, we are going to define this quantity here that we call Tour ratio. It's only we multiply for the entropy production rate in both sides of the inequality, and then we compute this quantity for different values of the energy gaps of the system and different values of the temperature. As you can see, the quantum absorption refrigerator is not able to violate the thermodynamic uncertainty relation. It's always above the bound, and it only saturates the bound in the point in which we change from one regime to another that corresponds to an equilibrium state in which we have zero entropy production. Okay, but this is probably my reaction when I see that. But then you're probably thinking, okay, but these are some configurations of the system. Maybe there exist some other configurations in which the quantum absorption refrigerator can violate the thermodynamic uncertainty relation. Okay, let's see that. Here I plot the different values of the histogram of the different values of the thermodynamic uncertainty relation for 10 to the 8 different configurations of the system parameters. And as you can see, the quantum absorption refrigerator is not able to violate the Tour in all the cases. So at this point, we can say that the quantum absorption refrigerator cannot violate the thermodynamic uncertainty relation. But well, okay, we have seen that the coherence have a clear effect in the thermodynamic outputs. So maybe my quantum system is better than its classical analog. So now we have to make this classical analog. What are the conditions that we are going to impose in a system to be a good classical analog? Okay, the first one is to have the same energy levels. The second one will be not having a steady state coherence. And the last one is to have the same populations in the steady state. By imposing these three conditions, at the end, what we have is two systems that have the same energy levels, have the same populations of the density matrix, and the only difference that we have between the two is the non-diagonal elements of the density matrix. Okay, now let's go into make our classical analog. So the same energy levels, we are going to consider the same system, for example, same energy levels, and then we need no steady state coherence. So for this, we are going to change the interaction Hamiltonian for a classical stochastic transition between the two levels that were connected by the interaction Hamiltonian. And then the last condition, for the last condition, we have to find what's the value of the probability rate for the both systems to have the same populations in the steady state. This is easy to see if we go back to the equations of motion of the system and we solve for the coherence in the steady state. And then we take this expression and we put into the equation for the populations. And we arrive to, these are the two populations that only depends on the coherence. And here we can see that the net effect of the coherence in the steady state is to have virtual jumps between the two levels that were connected by the interaction Hamiltonian. And we see that these virtual jumps have to occur with a probability rate given by this expression. So here we find the probability rate for our classical stochastic transition to have the same populations. Okay, with this, now we can solve the dynamics of the classical analog, compute the thermodynamic quantities, and compare with the quantum case. Here you can see in the e-axis the thermodynamic quantities for the case of the classical analog, and in the x-axis the quantities, the same quantities, but for the case of the quantum absorption refrigerator. As we see, the relation is a straight line which have a slope equal to 1. So we have found that the classical analog is able to thermodynamically emulate the quantum absorption refrigerator. So I have to take a moment here to talk a little bit about this. We are not saying that the quantum absorption refrigerator is not a quantum system. Indeed, it is a quantum system. There are some papers in which the authors see that this system presents entanglement for some values of the parameter, but we are saying here that the effect of the coherence in the thermodynamic outputs don't present any type of advantage over a classical system. So now with this result, I end like the first block of the thermodynamic operation, and now I want to jump into the optimization problem of the thermodynamic outputs of the machine. For this, we are going to employ the Pareto optimization criteria. Well, you're probably thinking, but what is a Pareto optimization problem? Well, the Pareto optimization problem is a problem, for example, I'm going to use, for example, the problem of minimize, sorry. So imagine that we want to minimize k different functions that are called objective functions that depends on n different values that are called design variables. Here, for us, this will be the thermodynamic outputs, efficiency, cooling power, fluctuations, and these will be the parameters of the system. So the Pareto optimal solution, broadly speaking, is the, well, in a mathematical way, there are the solutions that fulfills this relation, but broadly speaking, the optimal solutions are the ones that are equal or better than all the non-optimal solutions, but are strictly better than the not optimal solution in at least one objective function. We can see more clearly with some examples now. So this can be easily implemented in various forms in a numerical way, but also can be solved analytically. Indeed, we solve one Pareto optimization problem analytically in the main text, but here I don't have time to show the derivation, but if you want, we can talk about this in the questions. So let's apply the numerical Pareto optimization to our problem. For example, we can try to maximize efficiency and maximize cooling power in the machine. Here you can see the blue points represents all the different configurations that I can generate for the refrigerator for a fixed value of the temperatures in the environment. And as you can see, the numerical solution of the Pareto problem is this orange line that is connecting the point of maximum efficiency and the point of maximum maximum power. But we see that in the middle we have a whole branch of solutions that are objectively better, and in which we have some kind of trade-off between efficiency and cooling power, because here the only thing that we are solving is the optimization problem but giving more weight to one variable or another. So, but we have said that we have access to the fluctuations. So let's see what happens if I try to minimize fluctuations and maximize cooling power in the system. In this case, I obtain again a solution of the Pareto problem, which is a branch that connecting the point of zero fluctuations and the point of maximum cooling power. And in the middle, I have again a whole family of solutions given weight with different weights in the optimization process. But what happens if I now try to minimize fluctuations and minimize, for example, efficiency? In this case, we see that the solution of the Pareto optimization problem is only one point, the point of having Carnot efficiency, maximum efficiency, and having zero fluctuations. So at this point, we have solved all the possible two-dimensional optimization problems, but we can try to solve the total optimization problem. We can try to solve the problem of maximizing efficiency, maximizing cooling power, and minimizing fluctuation. In this case, we find that the set of optimal solutions is the total set of machines that we can generate. So we have this blue surface in which we have all the points that we can generate that are all the solutions that are all solutions of the Pareto problem. And in the border of this surface, we have here, for example, the solution of the optimization of cooling power and efficiency, and here the solution of optimizing cooling power and variance. And they meet each other in the point of maximum cooling power. So what we have seen here is that we, in the three-dimensional case, we only have trivial solutions for the total optimization problem. So maybe not. At this point, if you remember, I say that we have the temperature for the environment fixed. So we can try to change the temperature of the environment and see what happens with the Pareto problem. Here you can see, again, the blue points represents all the possible configurations that I can generate of the refrigerator, now changing the temperatures, and the colored surface, where the color bar means efficiency here, are the ones that are optimal, that are solution of the Pareto optimization problem. And we see that here we have a non-trivial solution. So we see that changing the temperatures, we can have access to a group of machines that are objectively the better machines that we can build for a same time task. For example, we have zones in which we are giving more weight to maximizing the power, or then we can move into the surface to go into points in which we have more efficiency, but sacrificing power, or then we can move to having high efficiency and lower fluctuations, but even sacrificing more power. Okay, so with this, I want to end the results that I want to show you here. I want to end with a briefly summary of all the results that we have seen in the presentation. The first was we see that the presence of coherence has a clear effect in the cooling power, the entropy production, and the precision in the quantum absorption refrigerator. Then we see that the quantum absorption refrigerator is not able to violate the thermodynamic uncertainty relation, the classical version of the thermodynamic uncertainty relation. After that, we compare with a classical analog, and we see that the coherent boost in the thermodynamic outputs is emulable by the classical analog that we create. And then passing to the optimization part, we find that we are not able to find non-trivial solutions for the three-dimensional optimization problem if we have fixed temperatures. But we see that if we change the temperatures in the process of optimization, we can obtain non-trivial solutions to total Pareto optimization problem. That means that the presence of optimal solutions highly depends on the temperature configurations of the system. So with this, my presentation ends. I hope you like it, and I will try to answer your questions.
Now it's time. So thank you for the presentation. Now it's time for questions. And I think that we should start maybe